In this video, I will show you how to move back and forth between component form and magnitude slash direction form, magnitude and direction. Component form involves rectangular coordinates, which is a fancy way of saying the x comma y that we deal with anytime we do a graph like this. But first, let's warm up with a couple of review problems. How would we find this missing side of the triangle right here? Well, from the perspective of the 54 degrees, the x is the adjacent side, while the 4 is the hypotenuse. Adjacent, hypotenuse. That's the cosine function. So I could say cosine of 54 is equal to adjacent over hypotenuse. Multiplying both sides by 4 gives me 4 cosine 54 is equal to x. And then I could just put that in my calculator. 4 cosine, wait, you know what? I need to make sure I'm in degree mode. I am. 4 cosine 54. Alright, that is 2.35. Okay, now how would I find this side of the triangle? Call it y. Well, from the perspective of the 54, the y is the opposite side. So I've got the opposite side and the hypotenuse. Oh my goodness, that's the sine function. So I could say sine of 54 is equal to y over 4. Multiplying by 4, so I would get 4 sine 54 is equal to y. And then it would just be a simple matter of putting this in my calculator. 4 sine 54. 3.24. Now, I want you to focus on this step in the process for a second. We have the horizontal labeled as x, the vertical is labeled as y. Imagine that the hypotenuse, let's call that r. R stands for radius. Imagine that this is the center of the circle, that would make this the radius of the circle. So we have x, y, and r. If I want the horizontal component, the horizontal component is always going to be r cosine theta. Alright, obviously this is theta right here. Alright, the horizontal component is always r cosine theta, and that's what we had right here. I wanted x, the horizontal piece, and it turned out to be 4 cosine 54. That's r cosine theta. On the other hand, focus on the vertical piece, which is right here. The vertical component is always r sine theta. And you can see that's just what happened here. 4 sine 54. That was r sine theta. So keep that in mind. Okay? Look at this problem. Let's see if we can use the shortcut that we just learned to find the missing sides, the horizontal component and the vertical component. Now look at this point right here. Imagine that this is the center of a large circle. That would make this hypotenuse the radius of that circle. Now the x is the horizontal component, and we have now learned that the horizontal component is always going to equal r cosine theta. Meanwhile, y is the vertical component, and we've now learned that the vertical component is always r sine theta. So x is going to equal 6.3 cosine 27, r cosine theta. And y is going to equal 6.3 sine 27, r sine theta. So x turns out to be 5.61 and y turns out to be 2.86. Now so far we've just been dealing with positive lengths because we were just dealing with sides of a triangle. Now I want to move this in the direction of vectors. So imagine that instead of a radius, I looked at this as a vector going from here to here. What we have just found will give us the component form of this vector. So since x is 5.61, but because it's going to the left, I'll go ahead and call it negative 5.61. The vertical component is 2.68. Because it is down, that's going to be a negative 2. Did I say 68? 2.86. So I'll say negative 2.86. All right. The point is we can use this process to convert from an angle and a magnitude to component form. Let's do the same thing back on the previous problem. If we consider this to be a vector instead of just a radius, then what we have is component form. Okay, the component form of this vector is 2.35 comma 3.24. All right, that was the horizontal component and the vertical component that we found using the same process. This one's in the first quadrant, so everything is positive, so that worked out nicely. Okay, so in a nutshell, if I want to find the horizontal component, it's always going to be r cosine theta, where r is the magnitude or length of the vector. And the vertical component is always going to be r sine theta, where r is the magnitude of the vector, the length of the vector. Now, in previous videos, we have also discussed if I need to find the magnitude of a vector and I'm given the component form, this is how I can find the magnitude, the square root of x squared plus y squared. And if I want to find the direction, I can use inverse tangent, but I have to be careful about what quadrant I'm in. So if we are given component form, we should be able to write magnitude and direction. If we are given the magnitude and direction, we should be able to write component form. Okay, so let's practice going in both directions. So here we are given component form, aka rectangular coordinates. So if I want to find the magnitude, I can just do the square root of negative 5 squared plus 4 squared. So that's going to be the square root of 25 plus 16. So that's going to be the square root of, what is that, 41. Alright, so there's the magnitude. Now, as far as the direction goes, I will draw a quick sketch to help me find the direction. If I'm going left 5 and up 4, that puts me in the second quadrant. Alright, so here's a vector in the second quadrant. I'm going to need to find the reference angle first, alright, because we are not in the first quadrant. We are left 5 and up 4. So I can use tangent. The tangent of the reference angle will equal 4 over 5. Alright, I'm dropping the negative sign because I just want the positive r value. R will then equal the inverse tangent of 4 over 5. And let's see, what's that? The inverse tangent of 4 over 5 is 38.66. Got to round up. 38.66 degrees. Now, the actual direction angle has to be measured from the positive x-axis like this. Let's call it theta. This theta was on its way to being 180 degrees, but we had to stop short by a value of r. So in other words, theta should equal 180 minus the 38.66. That's 141.34 degrees. That's the direction, 141.34 degrees. Alright, I see some graph paper over here. Alright, I think we're supposed to sketch it, both using component form and sometimes we call these polar coordinates. Alright, that's just a fancy way of saying that we will be using the magnitude and the direction directly to graph it. Well, using the polar coordinates, we've got, I think I'll graph it in standard position, so I'll start from 0, 0. I would go left 5 and up 4. So left 5, up 4. This would be my terminal point. Let's draw it. Okay, so this is what the vector would look like. I'm going to make it blue. Alright, so there's our vector u. And you know what? We should probably go ahead and label it while we're at it. So there you go, vector u. Now, let's graph the same vector using the magnitude and the direction. Well, you know what? If I'm going to do the magnitude, I actually am going to need a decimal approximation. So let's see, the square root of 41, alright, is approximately 6.4. Okay, so I need to go to 141.3 degrees, and then I need to go out 6.4. So let's see, 141. In fact, maybe I'll just write that down real quick. Alright, so here's the magnitude and the direction of the vector that we're going to graph on this neat circular graph. So each one of these angles that are pre-marked are increasing by 15 degrees. So I've labeled enough of them to contain the angle that we want. So we need to find our way to 141.3 degrees. So let's see. It's going to be somewhere between 135 degrees and 150 degrees. So it's going to be somewhere in here. And also we got to pay attention to the length. The magnitude you see is 6.4. Alright, so this would be magnitude 1, 2, 3, 4, 5. Maybe I should be counting by twos. 1, 2, 3, 4, 5, 6. I counted wrong. So this is magnitude 1, 2, 3, 4, 5, 6. The outer circle is 6, magnitude 6. Alright, so I need to go a little bit past that. So this would be about right. Okay, and now compare the angle that we just, the vector that we just created with the one that we graphed using component form. You can see that they are both pointing in the same direction and they have the same length, the same magnitude. Alright, so it is very, very consistent. So once again, this is another way of graphing vector u. Again, the magnitude and direction are also known as polar coordinates. For example 2, we are given the magnitude and the direction of a vector, also known as polar coordinates. And we are supposed to find the rectangular coordinates, in other words, component form. So we have now learned that we can find the horizontal component by doing r cosine theta. R is the magnitude. And we can find the vertical component by doing r sine theta. So that's all we have to do. So we'll do the magnitude cosine 200, and we'll do the magnitude sine 200. And that should give us the rectangular coordinates, the component form. So get ready. Let's see, 3.2 cosine 200. 3.2 cosine 200. Boom. That's negative 3.0. I'm going to go ahead and round this to one decimal place. So negative 3.0. Okay, and 3.2 sine 200. That is negative 1.1. Got to round up. Okay, so to the nearest tenth, component form would be negative 3.0, comma, negative 1.1. Very, very, very simple. Okay, so this will be a tiny vector to graph, but let's take a look at it in both versions. So if I want to do my component form, I'll go ahead and graph it in standard position. So I need to go left 3 and down a tiny bit more than 1. So left 3, down 1 and a bit would be about here. There's my terminal point. Let's draw it. Initial point, terminal point. Make it blue. Alright, there's our vector. Now, let's draw the same vector using the polar coordinates, the magnitude and direction. Okay, so here I've numbered my way around, increasing by 15 degrees every time, because that's how these are marked. So let's graph this vector. Standard position, of course. So first, I'm paying attention to the direction, 200 degrees. So that's going to be between the 195 and 210. It's a little bit closer to 195. So this is the direction. Now 3.2. So remember, this is 1, 2, 3 is right here. So 3.2 is just going to be a little ways past that. Okay, so here you go. Let's go ahead and make it blue. Alright, we have graphed this vector using the magnitude and direction. Again, compare the two. The directions are the same. The length or magnitude is the same. Okay, it's just two different ways of graphing the same vector. Example 3. Let's go again. We are given component form, rectangular coordinates. We can easily find the magnitude by doing 6 squared plus negative 8 squared. So that's going to be 36 plus 64. That's going to be the square root of 100. So the magnitude is 10. Not sure how that's going to fit on my graph over here. It's too big. Anyway, we'll do our best. Now, the direction. If I want to find the direction, I can do a quick sketch. like this. If I go right 6 and down 8, that puts me in the fourth quadrant, so I'm going to draw myself a fourth quadrant vector. Let's make a little triangle out of it surrounding the reference angle, and I can find the reference angle using the tangent. Okay, I went right 6 and down 8, so the tangent of r should equal 8 over 6. I'm ignoring the negative sign because I just want the positive value of r. So that means the tangent of r is going to equal 4 over 3. So that means the measure of r is going to equal the inverse tangent of 4 over 3. So that means that the value of r can be found on the calculator. So inverse tangent 4 over 3. 53.13. Now, the actual direction angle has to be measured from the positive x-axis all the way around. I'm going to call that theta. And theta should be, it was on its way to being 360 degrees, but it stopped short by the amount of r. So theta should be 360 minus 53.13. That's 306.87. That's the direction. Alright, let's go ahead and graph this vector using both methods. First of all, using the component form, right 6 and down 8 would look like this. Okay, right 6, down 8. Whoa! It had to move, didn't it? I think this is it right here. Now, graphing this using the magnitude and direction of 10, 306.9 degrees. Here I've labeled this quadrant increasing by 15 degrees each time. And notice the 306.9 degrees here, I've graphed it in between 300 degrees and 315. It's going to be pretty close to the middle. And the length, coming out to this outer circle, that's 6. So I had to estimate 7, 8, 9, 10 would be about here. Now compare this vector to the vector that we got when we graphed it using component form. You can see that they are the same direction and the same magnitude. So it works. Alright, let's do one more example. We are given the magnitude and the direction. So again, if I want to find the rectangular coordinates or component form, it's going to be r cosine theta will be the horizontal component, and r sine theta will be the vertical component. I'm using r to represent the magnitude of the vector. So this would be 4 cosine 72, and this would be 4 sine 72. So we'll just put these numbers in the old calculator. Okay, 4 cosine 72. That's 1.2. I'm going to round to 1 decimal place, so 1.2. 4 sine 72 is 3.8. Okay, so rounded to 1 decimal place, 1.2 comma 3.8 would be the component form or rectangular coordinates. Alright, now let's go ahead and graph using both methods. Okay, so if I were to go over 1.2 to the right and then 3.8 up, so 3.8, that would be right about here. Okay, that would be my terminal point, pretty close to it. So that's going to go like this. Okay, so that's how we would do it using the rectangular coordinates, the component form. Now let's look at the magnitude and the direction. Okay, so here we go. I'm going to start to graph my angle in my vector in standard position. Now here is 75 degrees, but our direction is 72, so it should be a little bit short of 72 degrees. Now the magnitude is 4, so this is 1, 2, 3, 4. So it should be about here. Okay, now compare what we graphed using the magnitude and direction compared with the vector that we got when we graphed the component form. You can see that they are heading in the same direction and they do have the same magnitude. So we're looking good. Hey guys, that's going to do it for this video. Go ahead and click over here to watch the next video and click over here to subscribe. That way you'll get every new video delivered right to your home screen.